So in this problem, we're given an and a3n, and then given both of these clues, we need to find a4n. So let's try to do just that. So we start with knowing an is equal to 10, and then a3n is equal to 24.4. So we know nothing about n, we know nothing about I, so we're going to have to try to find what I or n is using these clues that we're given. So if we express this in the formulas, we can see that the obvious thing we can do is to try to get rid of I and to try to find what v to the power of n is. So I can easily get rid of I by considering this ratio. So this is just equal to the formulas dividing each other. So i's, they cancel out. So I get something like this. And then now I'm going to use this formula to factorize the numerator. So you can actually factorize this term into something like this. So you can prove this by just expanding this part. So you can see that 1 is actually 1 to the power of 3. v3n is equal to v to the power of n to the power of 3. So we can actually use this formula. So here we get something like this after the factorization. And then these, they cancel out. So we get 1 plus vn plus v to the power of 2n. And then don't forget, on the left-hand side, we can find the numerical values of these expressions. So this is essentially 24.4 divided by 10, so it's 2.44. So now we actually have an equation. We have v to the power of 2n plus v to the power of n plus 1 is equal to 2.44. So v to the power of 2n plus v to the n minus 1.44 is equal to 0. And then this is actually just a quadratic equation. So in case you can't see it, I can let v to the power of n be equal to x. This is just x squared plus x minus 1.44. So if we solve this quadratic equation, we know what v to the power of n is. And then you can actually solve this quadratic equation by either you can substitute it into your calculator, or you can factorize it. So based on this factorization, either x could be 0.8 or it could be x equal to negative 1.8. And we know that this is ridiculous because I is going to be something that's positive, and then that means v to the power of n is always going to be positive. So x is equal to 0.8. So we know that v to the power of n is equal to 0.8. So how is this going to help us? So we can notice that we can actually express a4n as equal to an plus v to the power of n multiplied by a3n. And then you can reason your way through this by observing this diagram. So a4n, that's payments going from all the way from time 1 to time 4n, right? So this is payments from 1 to 4n. Now on the right hand side, first we have this component, an, so that is payments from time 0 to time n. And then we have a v to the power of n, so something is happening here, and then we're going to discount it back. So that something that happens over here is actually a payment, an annuity of 3n. So that's just more payments all the way from n to 4n. So this covers 3n. So this is exactly what it is, 3n. And then a3n, that's going to bring all these payments to time n, and v to the power of n is going to bring the amounts we have here back to time 0. And that is exactly equal to all these payments when you just group it all up into one annuity of 4n payments. So using this kind of verbal argument, you can actually prove this formula. The other way to prove this is, of course, to actually use their formulas. So if you write this out, it becomes rather obvious. These vn's, they cancel out. And then there's a 3n, there's n, so it becomes 4n. So these cancel out. So we get 1 minus v to the power of 4n divided by I, and that's just a4n. So this is like an algebraic proof. This is like an intuitive proof. So just pick one you prefer. So going back to the problem, we found that we know that an is 10, a3n is 24.4, and then we just found that v to the power of n is equal to 0.8. So just applying this formula, using your calculator, you can calculate the final answer to be equal to 29.52.